This lecture is on chapter 3, at least starting chapter 3, which deals with chemical bonds. As you might expect, your chemical bonds are basically the glue that holds the atoms together to form molecules. Before we start, however, let's do a quick review of what we have covered in the last lecture. We looked at the periodic table. So once again, make sure whenever you study, whenever you take your quizzes, whenever you take the exams, you have your periodic table available. Lots of information in that periodic table. As we can see, lots of trends in terms of properties of the atoms. Next, we looked at orbitals. Definition: orbitals are the regions outside the nucleus most likely to find the electrons. And remember that there are different sizes and different shapes for these orbitals, and different letters and different numbers we describe as quantum numbers. The electronic configuration or population of the atoms. Okay, so once again, there are rules that we'll have to follow to put the electrons in the orbitals. So don't forget those rules. Next, we looked at the atomic size, which is a property of the atoms, and there's a trend in the periodic table. So don't forget that. We also looked at the ionization energy. By definition, the ionization energy is the energy required to remove an electron from the atom. Of course, as you'd expect, it would be the outermost electron that can be removed. And there is a trend again in the periodic table that's observed for the different atoms in terms of the ionization energy. Okay, let's get into today's lecture. So what we'll look at today is a new term called the Lewis dot structure. We'll define the Lewis dot structure. We will use it in terms of making different chemical bonds and different ions. Next, we'll look at ions. We'll define the term ions. There are two types, cations and anions. So we'll define those, and then we'll apply that definition to solving different problems. We look at a rule here called the octet rule. As you can imagine, the octet rule deals with 8. So what we'll see later on is that it's a rule that states that there should be 8 electrons around atoms when it comes to forming molecules. And lastly, we look at ionic bonds. We'll discover that there are two types of bonds that make molecules or attract atoms together to form molecules, and the ionic bond is one. The other one is, of course, the covalent, but in this lecture we will cover the ionic bond. Okay, so let us start. G.N. Lewis was a professor at UC Berkeley years ago, and he made a very important discovery. You'll need your periodic table to fully appreciate this discovery. So if you do not have your periodic table handy, my suggestion is to pause the video and get one close to you, so you'll have to look at it while we go through this lecture. What Lewis discovered is that the noble gases, so you'll have to find that on your periodic table, which is in group 8 to the extreme right, they are extremely stable. In other words, they do not react with other atoms on the periodic table. Extremely stable. He looked at the electronic configuration. Remember again, electronic configuration is just a description of the electrons in the orbitals of an atom. What he observed for the noble gases was that the outer shell of these atoms, they were full. They contained the maximum number of electrons. Helium has 2 electrons, and the outer shell, of course, is just a 1s. It's full. If there were a third electron, it would have to go into the 2s. But the outer shell here is full. Don't forget this number here, 2, represents the number of electrons. Let's look at the other one, neon. He discovered or observed that the outer shell here again is full. Remember, the outer shell here has the same quantum number, or the valence shell. That's another term that we use for outer shell, is the valence shell. So you notice that it's full, because if there were another electron, it would not go into any of these orbitals here, but into the 3s. But the bottom line is it's full. The same here for argon. Another observation is that notice that these electrons here add up to 8. 6 and 2, 8. So now you can get an idea of where we're going with the octet rule, or where the octet rule is coming from. 8. The outer shell contains 8 electrons, and that seems to correlate with the stability of atoms. Of course, in life, in life and chemistry, everything wants to get to a more stable state. That's the driving force for most reactions and just about all aspects of chemistry, is to get to a more stable state. So one definition of stability here is a full outer shell of electrons. Just to refresh your memory, here is the group 8, and that's the outer, that's the noble gases. Okay, let's look here at a new term, the octet rule. What Lewis observed is that most atoms, a lot of the atoms on the periodic table, they want to achieve that electronic configuration of the noble gases. So here is how they can achieve that configuration. An atom can lose electrons to gain that electronic configuration of 8 electrons in the outer shell. If it loses an electron, that species is an ion because it's charged, and specifically it's a cation. So that's a positively charged species. Why positive? Because if you lose electrons, remember electrons are negative, the atoms on the periodic table are neutral. So if it loses a negative, it becomes positive. And that's called a cation. So be familiar with these terms. That's the way we communicate in chemistry, is by using these terms. Let's look at another concept here, and that is the gain of electron. So if you get an atom on the periodic table, and if you should put electrons into it, remember again, electrons are negative, that atom becomes negatively charged, and it's called an anion. So two important terms here. A cation is a positively charged species, and an anion is a negatively charged species. So that's the definition. That's the definition. Let's see if we can apply that definition to some atoms on the periodic table. So here we go. In losing an electron, sodium, so try and find sodium on your periodic table. Sodium is to the extreme left of the periodic table, column 1. Next, write out the electronic configuration of sodium, and here it is. This is the electronic configuration. If sodium should lose one electron in its outer shell, it acquires the electronic configuration of a noble gas, in this case neon. So in other words, sodium is very reactive because it wants to give up one electron to become the electronic, to achieve the electronic configuration of the noble gas neon. If sodium does that, notice sodium on the periodic table is neutral, but once it gives up its electron, it becomes sodium plus, sodium ion, more specifically sodium cation, as written here. Let's look at the opposite. Gaining an electron. So let's look at chlorine. Try and find chlorine on your periodic table. It is to the extreme right, okay, column 7, next to column 8. Let's look at the electronic configuration. Here it is. The outer shell here has 7 electrons. 5 and 2. 7 electrons. It would like to gain one more electron so it can achieve the electronic configuration of the next noble gas, which, as you can see on your periodic table, is argon. It can achieve that by gaining one electron. And as you can see, this is the a full octet of electrons. And as you can see also, this is the electronic configuration of argon. So let's do some terminologies here. Chlorine atom on the periodic table is neutral. If it gains one electron, which is negative, it becomes the Cl negative, or an anion, and the name of that is the chloride ion or the chloride anion. Okay, let us look at a question here just to make sure you have gained and understood that concept. Which is most likely true for an atom with 6 electrons? 6 electrons. Of course, let us think through that question. What it's asking is, it would like to gain the electronic configuration of a noble gas, which means that it needs an octet of electrons in its outer shell, which also implies that it can gain 2 electrons to get 6, or it can give up all 6 electrons to get a full shell. The most likely aspect is that it's very difficult to remove 6 electrons, but more likely to gain electrons. So let's look at the possible choices. It will gain 1 electron. More than likely not, because 6 plus 1 is 7. It's not a full octet of electron. It will gain 2 electrons. Gain. So that looks like a reasonable answer. It will lose 1 electron. If it loses 1 electron, it becomes 5. Not an octet of electrons. If it loses 2 electrons, it becomes 4. Still not an octet of electrons. So let's see what's the answer on the next slide here. So no surprise here. It would gain 2 electrons to achieve the electronic configuration of the nearest noble gas. Okay, let us continue, and let's look at naming some of the ions, in this case specifically the cations. We won't go into much details here because you will have this chart whenever you take your quizzes and your exam, and make sure you have it around. But the bottom line is the cations are typically formed from the atoms to the extreme left of the periodic table. So get your periodic table again, and you'll notice that these atoms, they tend to lose electrons to form cations. And it loses one electron to get H+. H+ will. Lithium will lose one electron to become lithium plus. And likewise sodium, as we have just seen. So those are really called hydrogen ion and lithium ion. Just put the name before it. Others that we'll see, magnesium here, will lose 2 electrons to gain the electronic configuration of the nearest noble gas, or to achieve an octet of electrons. So look at your periodic table carefully. In column 2, you'll find magnesium, and it will want to lose 2 electrons to gain the electronic configuration of neon. So go ahead and write the electronic configuration of a magnesium and prove to yourself that if it lost 2 electrons to become magnesium cation, it will be in the most stable state, or the electronic configuration of the noble gas. Let's move on. So what we'll do here is we'll just briefly look at some other atoms, and this time we'll look at atoms in this region of the periodic table, and call the transition metals. So let's look at some of the names here that are used. In naming these from the transition or the inner elements of the periodic table, here's some general guidelines. Sometimes we use Roman numeral to tell us or to communicate the charge on the atom or the ion. Another way is sometimes we use a term which ends in OUS or IC. For this class, however, we will more than likely use the Roman numeral to communicate the charge on the ion. Why is this so important? It's important because the transition elements, they can acquire different charges. The next slide shows that. So for example, copper can be copper 1, and copper can be copper 2 plus. So what we'll do is, instead of writing, we'll write here the Roman numeral 1, which will indicate it's 1 plus. Or we'll write the Roman numeral 2, which indicates it's copper 2 plus. You'll also see that we can use these terms here with the suffix OUS or IC. But we'll emphasize, or we will be using more the Roman numeral. Same for the iron. 2 and 3, because it has Fe3 plus or Fe2 plus. So look out for that. Whenever we're writing the names of these compounds, we need to put in the Roman numeral to tell us the charge on the cations. We'll discover why this is so important in a second, because we will have to make sure that a molecule in a bond, the atoms in a molecule, that the charges are balanced. Okay? Before we do that, however, let's look here at naming the atoms to the extreme right of the periodic table. They're called, of course, the anions. So if you have fluorine and it should in fact gain an electron, the name becomes fluoride. Okay, same for chlorine, it becomes chloride. That's why table salt is described as sodium chloride and not sodium chlorine, because it is, chloride is the more stable state of chlorine in terms of the anion, because it tends to acquire one electron to achieve the electronic configuration of a stable state. Okay, here's another concept we need to go into, and that's called the polyatomic ions. What you'll discover is that for some ions, it's not just one atom, it's not just one element making up that ion, but they are made up of more than one. That's why it's called poly. Again, you don't have to memorize this table. You'll have it whenever you take your exams or your quizzes. But just let's go through a couple of these. NH4 has a positive charge, one positive, and it's known as the ammonium ion. We know this one. The OH, two atoms here, two elements, oxygen and hydrogen, pulled together, they form a polyatomic ion. In this case, it has a -1 charge, and the name of that is a hydroxide. Of course, as you know from your high school chemistry, sodium hydroxide, because it has the OH negative. So again, here are some more examples. You need not memorize this, but the more common ones are ammonium and the hydroxide ions. Okay, let's look at the Lewis model here in terms of making ionic bonds, a bond. So let's just go over this again. So an atom may lose or gain enough electrons so that the outer shell is full. Another way of putting this, atoms will lose or gain electrons to achieve an octet of electrons. So in other words, we are creating here ions, the cation and the anion. As you can imagine, the cation is a positive charge and the anion is a negative charge. So an molecule is made up of an ionic bond that results from the attraction between the cation, which is positive, and the anion, which is negative. And that's by definition is our ionic bond. Okay, let us apply that concept. So here's an example. Lithium. So get your periodic table and find lithium. Here's the electronic configuration of lithium. If it should lose one electron, it achieves this electronic configuration here with this outer shell, 1s in this case, since it just has 3 electrons, full. But then again, it becomes lithium plus, your lithium cation. Let's go to the other end of the periodic table. Notice we're going from end to end. The other end of the periodic table will find fluorine. Here's the electronic configuration of fluorine. Notice it's not a full octet of electrons because this is the valence shell or the valence electrons, outer shell 2 and 2. If it should gain 1 electron, it now acquires the electronic configuration of neon. or the outer shell is now full. But in so doing, it becomes fluorine negative. Of course, as we just discussed, you do not say fluorine negative, but you say a fluoride ion. Because of the positive and the negative, it attracts here to form a molecule, lithium fluoride, and the bond that holds the lithium attracted to the fluoride to make that bond is called an ionic bond. Same here. Another example. We have sodium. Here's sodium atom as it appears on the periodic table. Notice here that the outer shell here is not full. If it comes in contact with a chlorine atom, notice again the outer shell is not full. So this electron can be given to the chlorine atom, and if that happens, the chlorine atom now has a full octet of electrons and becomes the chloride ion. And of course, since sodium has lost one electron, notice this electron is lost, this is now your full octet of electrons right here, 6 and 2, 8, and that's now acquired a positive, so that's sodium ion. Here's another illustration. One electron from sodium goes to chlorine to get that octet of electrons here, and it's described as the chloride anion with a negative charge. And since sodium has lost an electron, it acquires a positive charge, and because of the positive and negative charges of these two species, that's the ionic bond that holds these two ions together to form a molecule. Let's look at another term, a new term for us, electronegativity. Sounds like a big word, but it's really not, because if you look at it, it's just basically the potential of an atom to attract electrons to itself. The attractions for electrons. Electronegativity, electrons. Okay, so atoms to the extreme right of the periodic table, as we have seen, tend to want electrons so that it can achieve the octet of electrons. Atoms to the extreme left of the periodic table tends to want to give up electrons. Notice it doesn't want to attract electrons. So there's a trend that we can see on the periodic table. Electronegativity increases in this direction. That means that this atom here is more electronegative than this atom over here. Of course, if you look at your periodic table, this is fluorine. So it wants to attract electrons to gain, or one electron to gain that electronic configuration of the nearest noble gas, or the most stable electronic state, or an octet of electrons. Over here, as you can see, this is lithium, and it wants to give up an electron to achieve the outer shell of helium. So this is not electronegative. These elements over here are not electronegative, whereas these elements over here are electronegative. So the most electronegative atom on the periodic table is fluorine, and the trend is in this direction and of course this direction. So given these two atoms, this atom here, fluorine, and chlorine, the question is, which is more electronegative? Based on this trend, this atom is more electronegative, fluorine. So look at your periodic table again and use this trend for electronegativity to determine two atoms. if you have two atoms, which is more electronegative? As you can imagine here, just to a summary, ionic bonds are made up of an ion, anion, and a cation. We know how to make these cations, and we know how to make these anions. So don't forget, to make the anions, they are made from the more electronegative atoms on the periodic table. That's the atoms to the right. To make the cations, they are made from the least electronegative atoms, or the less electronegative atoms of the periodic table, or the atoms to the left of the periodic table. Once these anions and cations are made, they form an ionic compound. So sodium chloride, table salt, is an ionic compound. Okay, let's see here, just some examples here as we close. So we have here lithium to the extreme left of the periodic table. Try and find that on your periodic table. It will form lithium plus. Bromine, which is to the extreme right, well, to the right of the periodic table, it will form the bromide anion because it wants electrons. It's electronegative. And of course, it will form here lithium bromide. An important aspect here, try and find barium on your periodic table. Okay, it's down to the bottom, but to the left. And it's in column 2. So that indicates that it would want to give up 2 electrons to form Ba2 plus. Notice 2 plus. If it comes in contact with an iodide anion which has 1 plus, it forms a molecule. But notice the molecule is written as Bai2 and not Bai. Why is that? Because the charge on iodide is -1. It will always be -1. The charge on barium is +2. We know that a molecule is neutral. So, to compensate, there are 2 iodides for each barium. So that's why we have a 2 as a subscript. Just to reinforce that concept, here's another example. Find aluminum on your periodic table. You'll notice that aluminum here is to the left. Well, it's kind of in the center, but it will lose 3 electrons to form Al3 plus. Notice 3 plus. If it comes in contact with a Cl negative, and Cl will always be -1, the molecule that's formed, or the ionic compound that's formed, will be aluminum chloride. However, because this is 3 plus and this is -1, and we know that aluminum chloride is neutral, it will require 3 chlorides to balance that +3. So again, in writing these ionic compounds, make sure you include the appropriate subscript so that it's shown as a neutral molecule. Just to make sure we have that concept, let us answer this question. What is the formula of the compound that's made by potassium and chlorine? Now this is a question that really gets to the concept to make sure we understand the concept that we just went over. So get your periodic table. Potassium is to the left. And as you can see, it's in column 1. So it would want to lose 1 electron. So here it would want to form here K plus. Chlorine is to the extreme right of the periodic table. And to achieve the electronic configuration of the nearest noble gas, or an outer shell of 8 electrons, it would want to gain an electron. So as you can tell, it wants to achieve Cl minus 1. So the negative 1 and the positive 1 will form a compound. In writing compounds, the cation comes first and the anion comes next. So you always want to write your positive ion followed by the negative ion. So what you'll have to do is to look at these choices here and determine which one is appropriate. Let's start at the bottom. K2Cl. Cl is just negative 1. So it does not need 2 pluses to balance. KCl3. K is a positive 1. So it does not need 3 negatives to balance. K2 plus. K plus again is positive 1. So it does not need 2 negatives here to balance it. So more than likely it's KCl. Let's see what's on the answer here. And it's not a surprise that this is the answer. And notice again the way it's written. It's K cation followed by Cl anion. So always write your cation first followed by the anion. Okay, just some other examples here. We did aluminum trichloride. Don't forget the 3. Lithium bromide, we actually did. And here are some other examples here. And just looking at this, we won't get that complex, but let us look at KCl again. So K is at the extreme left and Cl is at the extreme right. So K would want to form +1 and Cl would want to form Cl1. So therefore it's just KCl. Let us see here some more examples. So here's what we were talking about earlier. And let us see if we can find an example here. Let's look at this one. So if you asked, copper is a transition metal and it has a charge of 2, which is indicated here by the Roman numeral 2. So that's 2 plus. And it reacts with oxygen. Looking at the periodic table, you can see that oxygen would prefer to gain 2 electrons. So it becomes O2 negative. O negative. So it becomes O2 negative. That's for the oxide. And of course, you know, the copper here is Cu and it's 2 plus. So the question now is, how do you write these 2 elements or these 2 ions, a cation and an anion, to form an ionic molecule? And of course, here it is. It becomes a little trickier if you're looking at copper +1. As you can see, this is now copper +1, Cu +1. If it combines with oxygen, which is O2 negative, you can see that it would not be the same formula. So you would need 2 of the coppers to balance out this negative charge, this -2 over here. So that's why that is written as Cu2. Notice the subscript 2. So again, be prepared to write the formulas of ionic compounds and make sure that the charges are balanced based on the charge of the various ions. Okay, I think we have a couple more examples here, and we won't go through these in details, but here is, let's look at a polyatomic one here, copper sulfate, for example. So the copper has A2, and looking back at the polyatomic, this is a polyatomic, and it's called the sulfate, and it has a -2. So go back and look at that table that we gave you. This one is -2. And since this is +2, we can write it as CuSO4. So that's one example. So you can work through the others on your own. We will stop here because the next lecture has to do with covalent bonds. So go through and work these. Since I'm here and I've just seen this one here, this is ammonium sulfate. So once again, remember that this is the ammonium from the polyatomic. It is +1. So go back and check that on your table. The hydroxide polyatomic is -1. So this becomes the formula NH4OH. Okay, so this concludes this lecture. So go back and refresh your memory of the various concepts that we looked at, but most important, make sure you can apply these concepts to solving various problems. I will post the other lecture on chapter 3 shortly, and these two lectures will be all that we cover in chapter 3. And of course, as I mentioned in my email to you, that chapters 1, 2, and 3 will be on our exam, which is scheduled for Thursday. Okay, continue to study hard.